In this lecture, we're going to be learning about unique pointers. And unique pointers are an effort to make memory management easier in C++. And unique pointers help in two ways. The first way they help is that at any given moment, there can only be one pointer managing the memory. And the second point is that when the unique pointers goes out of scope, the memory is going to be automatically released. This is going to relieve the work from us to remember to release the memory through the delete operator, but it is also possible to completely avoid the new operator. And we're going to completely let the C++ system manage the memory for us. Let's see how this works in practice. Okay, so the first thing we need to do is to include the memory header. And this is where the smart pointer stuff live in the C++ standard library, so we have to remember this. And before we talk about unique pointers, let's remind ourselves of ways we have been managing memory so far. The first thing we have done is manage memory through stack variables like this. And we could set up a variable like this, use it, and when the variable goes out of scope, it's going to be automatically released by the C++ system. So we don't really need to do any active memory management here. The C++ system is going to do all the work for us. And this is really what we want to simulate with smart pointers, but we're going to be using heap memory with smart pointers. Okay, so another way we have seen to manage memory is to use pointers or row pointers as we see here. And we have to use the syntax you see here. We say our type, and we say that it is a pointer. We give the variable name, and then we use the new operator to allocate space on the heap. And once you do this, we can use the pointer access operator to access the member variables on the type that we just allocated on the heap. We can also dereference stuff to get direct access to what is pointed to. We can use pointers like we have been using them before. But another important thing we need to remember is to release the memory once it has already been used. And this is the point that trips off many people. In a lot of cases, some people are going to forget to call the delete operator and they are going to leak memory. This is the problem that smart pointers are trying to solve. With smart pointers, you don't have to explicitly call the delete operator. The memory is going to be released automatically when the smart pointers goes out of scope. So let's see how this works with unique pointers. Okay, so here we have a few examples of how we use unique pointers. The first way we can use them is to manage previously allocated heap memory. For example, here we have a dog object. We have a pointer to that. It has been automatically allocated for on the heap. And we are setting up a unique pointer here. We say std unique pointer. We say angle brackets here. And inside that, we're going to put our type. So this is a unique pointer to dog. So that's how we say it here. And we're going to give it a name. And then we're going to say the memory that this unique pointer is going to manage. And it is going to be managing previously allocated memory on the heap. So this is something we can do. But once we do this, please remember to no longer use this row pointer here, because if you use it, you're just going to disturb what the unique pointer here is doing. My best practice is to directly set this pointer here to null pointer so that it is really not pointing to this memory anymore. Because from this point on, this memory is owned by this unique pointer here, and the row pointer we had before really has no more business managing this memory here. Another way we can use unique pointers is how you see here. We say std unique pointer, we say the type, we say the variable name, and then we call the new operator inside our brace initializer here. This is going to work. We can also have unique pointers to fundamental types. You see, this is a unique pointer to int, as you see here. And really the syntax is the same. We are saying new int inside our brace initializer here. We can also set up a unique pointer and initialize that with null pointer, and we can make it manage some memory later, and we're going to see how this works in a minute, but note that this is something you can do. Okay, so once we have our unique pointer set up, we can really use it like we have been using all pointers before. We can call stuff using the pointer call operator. We can dereference to do things with the data that is pointed to. So for example, you see the unique pointer to int here is being assigned a value. This is something you can do. We can dereference and print stuff. But another thing we can do is get access to the managed row pointer using the get method here. And this is something we can do. This is going to be useful if, for example, you are using an API that uses row pointers. You can get the row pointer, but please remember to not use it to manage memory. Please let your unique pointer manage the memory for you. This is something you can do. Okay, so it is also possible to completely let the C++ system call the new operator for you. The way you can do that is to go through std make unique to allocate memory on the heap. This is going to internally call the new operator for you, but your code is going to be much cleaner because you don't want to be calling the new operators yourself. You want the C++ system to help you allocate memory, and you can do this through the std make unique facility here. So the syntax is really what you see here. You say std make unique, you say angle brackets. Inside, you say the type you want to allocate, and you can pass data to initialize the memory that was allocated on the heap. For example, here, if we pass the data here, the data is going to be used to initialize the dog object that is created on the heap. And that data is going to be pointed to by the unique pointer that we have here, updog7. And we can use it to do stuff with the data that we are pointing to. For example, we can call stuff on the shared pointer. We can dereference and change the value inside. We can really do all kinds of crazy things. We can also use the get method to get to the pointer that is pointed to. So know that you can really do this. But you don't have to call the delete operator on these pointers here. When the unique pointers here go out of scope, the data is going to be automatically released. And when we hit Visual Studio Code in a minute, you're going to see that the destructors are going to be called without us to have to explicitly call the delete operators. And this is really cool. One thing you should know is that because these are unique pointers, you can't really copy them. And to really show the point here, let's suppose we have a unique pointer, updog8 here, and it is pointing to a dog object, which is initialized with dog8 here to really make this super clear. We can do stuff with this pointer. For example, we can call methods on it. We can use the get method to get to what is pointed to. We can really do all kinds of crazy things. But what we can't do is use our data here to initialize other unique pointers. For example, if we do something like this, we're going to get an error because you can't really copy unique pointers. They are unique, and at any point, we can only have one unique pointer pointing to that memory. That's why C++ is enforcing this here. We can't also try to do the same thing through copy construction. If we do this, we're going to get an error because we can't really have two unique pointers pointing to the same memory address. So this is not allowed. If you do this, you're going to get an error. But one thing we can do is move ownership. And what we really are saying here is that the first pointer is going to give up memory management rights to another unique pointer, and it's going to be reset to null pointer, and the other pointer is going to take over the job of managing that memory location. The way we do that, here we have a simple example. We have a unique pointer, updog11, which is managing this object here. But we set up another pointer, updog12, which is going to be managing that memory. We give up memory management rights using the std move facility here, and we pass the pointer that is giving up its rights. It's going to be transferring the memory management rights to updog12 here, and from this point on, updog11 is not going to be pointing to this memory anymore. It's going to be automatically reset to null pointer. From this point on, we're going to be using updog12 to manage this memory here. For example, if we print dog here, we're going to be printing dog11. If we use the get method, we're going to be getting the row pointer that was pointing to dog11. And if we try to use the pointer in updog11, we're going to get the pointer which has already been reset to null pointer. We're going to see this when we hit Visual Studio Code in a minute. But know that we can give up our memory management rights through the std move facility, and we have to specify the pointer we are giving up the rights to through the syntax you see here, and this is going to work. Another thing you should know is that we have the option to reset our unique pointers. For example, we can have a unique pointer here. If we call reset, this is going to do two things. This is going to release the memory, and it's going to set the pointer to null pointer. And from this point on, this unique pointer is no longer going to be managing this memory here. And we can use this to our advantage. We can check if this pointer is pointing to something. If it is pointing to something, we can try and do something with that pointer. If it's no longer pointing to something, we say this pointer is not pointing to anything useful. And we're going to print the memory location to see that it is really not pointing anywhere. So this is all I think you need to know about unique pointers. Now that you know this, we're going to head over to Visual Studio Code and play with this a little more. Okay, so here we are in our working folder. The current project is unique pointers. We're going to grab our template files and put them in place. Let's do this, unique pointers. And we are going to open this little guy in Visual Studio Code by dragging and dropping here. This is going to give us the main CPP file that we can play with. We're going to remove what we don't need here. And the first thing we want to do, because we want to be doing stuff with smart pointers, is to include the memory header. So let's do that. We're going to say memory. Let's go up a little bit. Okay, so another thing we want to do is to put in a custom type that we're going to be using to really learn about unique pointers here. We're going to put in a dog class. So let's do that. We're going to put in a header dog.h, and we're going to put in a CPP file for that. We're going to say dog.cpp. I am going to grab a class that is lying on my drive here and use this as an example. So this is a dog class. We have our include guards here on the top and the bottom. We also have a few headers included, and we have a dog class. Nothing really special here. We have a constructor, we have another constructor which is defaulted, we have a destructor, and we have a single member variable which is going to be the name for the dog. Its type is a string. And we have a few member functions here. We have one to print the dog information, we have one to get the name, and we have one to set the name. Nothing special here. We also have an implementation file here that is going to contain the implementations for our constructor and destructor. And this is really all. Now we can head over to the main CPP file, include our dog class, and we can close the left sidebar here because it is just eating up space that we can use to make things better. Okay, so now that we have this in place, we can use stack dog variables. For example, we can set up a dog object like this. Once we have this set up here, we're going to be able to call stuff on the dog object here, but when it goes out of scope, we're going to see the destructor for this little guy called here. So the memory is basically going to be managing itself. All we have to do is specify that we want a dog object here, and when this goes out of scope, the destructor is going to be called. Let's see what we are doing in the destructor. We are saying that the destructor for some dog was called. So let's build and see the destructor called here. And we should go down here and say that we are done. To be able to really see this, let's do this. We're going to come back and put an exclamation mark here and say stdendl. I think this is going to do. Let's build this with GCC. We're going to see that the build is good. And let's bring up a terminal so that we can really run and play with this. We're going to clear and run rooster. We're going to see that the constructor for a dog was called. As you see here, we're going to print the dog information, and this is going to print the data here, and it's going to say done. Okay, so we're going to say done here, and after done, we're going to hit the end of the main function here, and we're going to say that the destructor for our dog object was called. So this is really cool. For example, if we take this thing and put this inside a nested scope like this, I want you to see this. We're going to put this inside here. And if we try to run the code now, we're going to say hitting outside scope. Okay, let's kill the terminal here so that you can really see what is happening. We're going to hit the main function here. We're going to do stuff outside the nested scope here. But once we hit the nested scope, we're going to set up this dog object here. This dog object is going to be scoped or constrained inside these curly braces here. And once we hit the closing curly brace, this dog object here is going to die. So we're going to call the destructor. We're going to see the message here, and then we're going to say that we are done. Hopefully, this really proves to you that the C++ system is going to kill the object or the stack objects here when we hit the scope where the object is leaving. And this is a property or a built-in property for stack variables, as you see here. We're going to bring up a terminal and we're going to build with GCC so that you can really see this happening. You're going to see that the build should be good. So let's clear and run Rooster. You're going to see that we say the constructor is called, because we are setting up a dog object here, we're going to print information through this statement here on line 13. Then we're going to hit the end of the scope that we have nested in the main function. That's going to cause for the destructor to be called. Then we're going to say that we just hit the outside scope here, and the program is going to end, and we're going to say done here. So this is a feature we have for stack variables, and the memory is going to be basically managing itself. Please know that this is what we want to simulate with heap variables through smart pointers. I am going to comment this out because we're going to see another way we can do these things. We're going to go on top here and say stack variables, or we can even take this and move that outside our nested scope here and put that to the outside. I think this is going to do. And we're going to go down and comment this out. Okay, another thing we have done is use row pointers to manage our memory. And let's uncomment this because I don't want to type all this. Let's close the terminal here. We don't need it. And what we're going to do is to set up dog objects on the heap. And the syntax we use to do this is what you see here. And we can do the same thing for fundamental types. For example, here you see we are allocating memory on the heap, and the memory is going to be containing an integer, as you see here. Once we have the memory, we can really use it through the pointer access operator. We can dereference. We can really do all kinds of crazy things. But one thing you have to remember is that you have to release the memory explicitly through the delete operator. If you don't do this, you're going to leak memory. For example, for the dog object here, we're going to see that if we say delete pdog2, this is going to call the destructor. Okay, so this is something you need to know. If you don't do this, the destructor is not going to be called, and you are going to leak this heap memory here. Let's build and run this. We're going to use GCC to do that. Okay, the build is good. Let's bring up our other PowerShell terminals. We're going to clear and run Rooster. You're going to see that we say the constructor is called for dog. We are printing the dog. We're going to say the values we have in our pointers. For example, the integer is going to be 100. The value we have inside the integer is going to be living at this memory address because we are printing that right here on line 30. And we're going to call the destructor for dog. We don't see the destructor for a fundamental type, but know that it is being released from the heap as we already know. But one thing I want you to see is that if we don't explicitly call the delete operator, we're not going to see the destructor called, and we're going to be leaking memory. Let's build again. We're going to build with GCC. You are going to see that the build is good. We can bring up one of our PowerShell terminals. We're going to clear and run Rooster. And once we do this, you see the constructor is called. We are printing the dog. We are going to say the value in our integers. We're going to say the address where our integer is going to live. But see that the destructor is not being called, even if we explicitly set up a dog object on the heap using the new operator here. Please remember that if the destructor for a dog object is called, it's going to say the message here, but we're not seeing that here on our terminal. And this says that the destructor was never called, and we have leaked the memory that we have allocated for here. This is something that many people forget to call the delete operator. If you happen to be doing a really complex application and these pointers are really being spread across multiple files, it is really easy to forget to release memory like this. And this is really where unique pointers are going to shine, or shared pointers in general. Because the core design principle for shaped pointers is to automatically release memory for you without having to call the delete operator explicitly yourself. So let's comment this out and really show you that we can use unique pointers to make this easy. We're going to comment this out. And then we are going to bring in code that uses unique pointers to make things easier. We're going to uncomment what we have here. And we're going to kill our terminals because we don't need them anymore here. So we're going to say that this is going to be using unique pointers. We can set up a doc object through row pointers as you see on line 41 here. This is the syntax you already know. But the most important thing I want you to see is that you can use a unique pointer to manage the previously allocated memory here. The syntax to do that is really simple. You say std unique pointer, you say the type that you want the unique pointer to point to. You say the variable name, in this case it is updog4 here, and we say the pointer that we want this to manage. Once you do this, the job to manage the memory that was previously allocated here is taken over by the unique pointer here. And we say that in a comment here. Once we have this unique pointer, you shouldn't really use pdog3 anymore because this memory is managed by the unique pointer here, and it is a good practice to reset pdog3 to null pointer once you do something like this to avoid further problems when somebody tries to use this pointer here. Another thing we can do is explicitly call the new operator in a braced initializer as you see here. We have seen this in the slides. We can also do something we have on line 46 here for fundamental types. This is going to work. We can even set up a unique pointer which is not going to be pointing to something just yet. We can just put in a null pointer and say that we're going to give this little guy something to manage later, and we're going to see how we can do that later in the chapter. Once we have our unique pointers, we can really do whatever we want with them. For example, we can use updog5 here to print the dog information. This is going to work. We can go through up2 and change the value inside. For example, we can change that to 500. This is going to work. We can even get the row pointer that is managed by the unique pointer through the get method here. One thing you should know is that when all these unique pointers go out of scope, we're going to see that the structure is called, and this is really cool. To really prove this, we're going to put these guys in a nested scope. So let's put in a pair of curly braces here, and we're going to grab everything we have on top here, and we're going to move them inside. Let's make sure this is aligned properly. And we're going to put in our data here, which is going to be living in a nested scope. You should really know this. And then we're going to say hitting the outside scope. And one thing I want you to see here is the constructors called for dog. We're going to see the constructor for dog3 called. We're going to see the constructor for dog5 called here. And then we're going to see the destructors for these guys called. And the dog5 destructor is going to be called first. And the destructor for dog3 is going to be called last. This is something I want you to see. We want to be able to see this information for fundamental types because they don't really have destructors that we can use to see this information. But note that the memory is going to be automatically released by the C++ system, and this is really cool. Let's bring up a terminal we can use to see these things. Okay, so we have that here. We can now run the task to build with GCC. The build should be good. As you see here, we're going to clear and run Rooster. We're going to see the constructor for dog3 called. We're going to see the constructor for dog5 called, and that's part of the call that we do here with new, and the other one we do with new here on line 47. So you should already know this. We're going to do whatever we need to do inside. For example, we're going to print information on our dog5 here through the line here. And then we're going to say the data we have in our unique pointers to fundamental types. We're going to see that we have the value 500 inside, and that's what we have right here because we changed the data to 500. So you see the data here. We're going to say where the integer is going to be living through the line here. Then we're going to hit the end of the nested scope here. This is going to code for the memory to be automatically released by the C++ system. And for our Doug objects, we're going to see the destructors called. We see the destructor for Doug5 called here, which is really what we expect. This is the object we allocated for on line 47. Then we're going to see the destructor for Doug3 called, which is what we set up on line 43 here, and let the unique pointer on line 44 here manage. And then we're going to hit the outside scope, and we're going to be really done with this program here. And please notice that the destructors are called, but we didn't have to explicitly call the delete operator to release memory as we did with row pointers before. This is a call feature of unique pointers as we see here, and this is really cool. So let's comment this out. We are going to keep learning about unique pointers and seeing more things about them. Let's go up and really comment this out. The other thing you need to see is that you can completely avoid using the new operator in your new modern C++ code. If you are using unique pointers, you can use std_make_unique to allocate your heap memory, and the syntax is what you see here. You say std_make_unique, you say your type in angle brackets here, and then you put the data you use to initialize your objects in a pair of parentheses as you see here. This is going to call your constructor with the data you have in here, and you're going to have a Doug object managed by this unique pointer, which is updog7 here. We can use this unique pointer to do whatever it is we want to do. For example, we can print information about our dog. We can even set up a unique pointer to a fundamental type. For example, pint3 here is a pointer to a fundamental type. We can dereference this and do whatever it is we want to do. But once this is done, memory is going to be automatically released when these unique pointers go out of scope. For example, here you see we are not explicitly calling the delete operators, but once these unique pointers go out of scope, the destructor for the Doug object here is going to be called, and we're going to see it called for Doug7 here. Let's build and run this so that you can really see this. We're going to build with GCC. You're going to see that the build is good. We can bring up a PowerShell terminal here, and we're going to use that to play with this. We're going to clear and run Rooster. Once we run Rooster, you're going to see that we have a constructor called. We're going to print information for Doug7 here. We're going to do whatever it is we want to do. But at the end, you're going to see that the destructor for Doug is called. So our memory here is being automatically released, and this is really cool. Please note that the syntax for std_make_unique is only possible if you are using a C++ version greater or equal to C++ 14. So if you are on C++ 11, this is not going to work. You will have to call the new operators explicitly yourself. But we are using C++ 20, so this is going to work, and this is really cool. Let's comment this out because we still have a few things I want you to see. And what you should know is that you can't really copy unique pointers. That's even the name. They are unique because we can only have one pointer pointing to a memory address at any given point. So here we have a bunch of unique pointers. We have a unique pointer to Doug, and we are using this pointer to do stuff. We are saying print Doug here. And we can even get the memory address where this thing is living, so you should really know this already. But what we can't do is use this unique pointer to initialize another unique pointer. This is what we are trying to do here, and you see we have a squiggly line. Visual Studio Code is already hinting that we have a problem here. What we are trying to do is copy a unique pointer. We are trying to copy updog8 into updog9. This is something that doesn't really make sense. This is a unique pointer, and we are trying to make two unique pointers point to the same memory address. So C++ is going to prevent us from doing this. We're going to get a compiler error if we're trying to do this. We can't even do the syntax we have on line 90 here because this is trying to copy a pointer through copy construction. This is not going to work. We're going to get a compiler error, and you should know that this is not going to work. You're going to get a compiler error. So if we try to do this on custom objects like Doug objects, we're going to see that the constructors or the copy constructors have been deleted. And this is not going to work. You shouldn't really do this. This is the message here. We're going to bring up a terminal because we want to see the compiler errors. We're going to run this through GCC. And if we do this, we're going to get a bunch of compiler errors. Let's go up and really show you this. And you see that the method that would allow us to do this is really deleted. This is the message here. Okay, if we go down here, we're going to see that it says use of deleted function, and this is a copy constructor for this unique pointer here, and it has been deleted. You shouldn't really do this. Let's comment this out and really show you that the code is going to work if we don't try to do any copies on our unique pointers. Let's build again. And we are going to see that the build is good. If we clear and run Rooster, we're going to see our information here. We're going to have a constructor for our dog, and we're going to see the destructor called, and this is going to work really well. This is what we expect. So you shouldn't really copy unique pointers. But one thing you can do is move ownership and give up memory management rights to another unique pointer. And we are going to go down and put in a piece of code to play with that. So we have a unique pointer, updog11 here, which is managing the dog object, which has the data dog11 in. And inside our nested scope, we're going to set up another unique pointer, which is going to move ownership of this memory object to another pointer. And we say that through std move, a facility we have in the C++ standard library. Once we do something like this, memory management rights to this dog object are going to move to updog12 here. And we're going to be using updog12 to manage the memory that was previously managed by updog11. I really hope this makes sense. So if we print dog through updog12, we're going to be printing information about dog11 here. And if we print the memory address, we're going to be getting the memory address that was previously managed by updog11. But updog11 is now going to be pointing to null pointer. If we try to print its information, we're going to see that. But we can even try to do something like this. We can say if, okay, let's say stdndl on top here. So this is something we can do. Now, when we do std move, ownership is going to move to updog12 here, and updog11 is going to be reset to null pointer. This is really cool, and this is something you can do if you need this kind of setup in your C++ programs. So let's go outside here and say that we have hit the outside scope, and we're going to say stdndl here. Okay, so let's build and run this. We're going to build with GCC. We're going to see that the build is good, so we're going to bring up our PowerShell window here. We're going to clear and run Rooster. Now we're going to see that the constructor for dog11 was called because we just allocated memory on the heap through std make unique. We're going to print information about our dog inside our nested scope here. You see that ownership has now moved. You see we are printing dog11, but notice that we called the print dog method on updog12. Hopefully this proves that ownership for this dog object has moved to updog12. We're going to print the memory address, and we're going to see that here. But if we print the memory location where updog11 is pointing, you see that we are going to get 0 here, and this proves that it is pointing to null pointer. But we can even use our if statements here, and you're going to see that they are going to say pointer 11 is pointing to null pointer, as you see here. And this is coming from this statement here. Hopefully you can see now that ownership has moved to updog12 and updog11 has been reset to null pointer. So once updog12 goes out of scope, the memory it is managing is going to be released, and we're going to see that we're going to call the destructor for dog11 now, and then we're going to hit the outside scope. And this is what I want you to see here. So again, the message is that we can move ownership of the data that a unique pointer is pointing to and move the memory management rights to another pointer, which is what we are doing here on line 98. This is really what I want you to see here. We're going to comment this out. There is one piece of information I want you to see before we close this lecture. And that is that you can reset a unique pointer and release its memory if that's what you want to do in your application. Here we have a unique pointer that we are allocating for on the heap using std make unique. The data inside is going to say dog13. And once we call reset on this unique pointer, notice that we are using the dot operator because we are trying to use the dog pointer itself. Once we do this, the memory is going to be released and the pointer is going to be reset to null. If we try and see what the dog pointer is pointing to now, we're going to say the pointer is now null because it has been reset. Let's build and show you this. We're going to build with GCC. You're going to see that the build is good. We're going to bring up a PowerShell window. Let's do that. We're going to say new terminal. This is going to open our window here. We're going to clear and run Rooster. We're going to see the constructor for dog, and then we're going to see the destructor called immediately because we are resetting the memory here. Okay, so this is going to release the memory. This is going to call the destructor. And then if we try and use this in this if statement, we're going to see that updog13 is now pointing to null. And that's what we see here through the get method here. And this is really cool. This is really all I had to share in this lecture. I apologize, this lecture turned out to be lengthy, but you really need to see this information in one piece because that's going to make it a little easier to digest. We are going to stop here in this lecture. In the next one, we're going to see how we can use unique pointers as function parameters or return types in functions. Go ahead and finish up here and meet me there.